Hey everyone, and welcome. Today, we're going to pull back the curtain on artificial intelligence and take a look at the actual blueprints, the core designs that give modern AI its incredible power. So let's dive right in.
I mean, it really does feel like magic, doesn't it? You hold up your phone, it unlocks in a split second. You ask a chatbot a crazy question, and it spits out a perfectly coherent poem. How on earth does that actually happen?
Well, the secret here isn't some single all-powerful program. It's more like a collection of specialized digital brains. We call them neural networks, and each one is built from a unique blueprint, making it perfectly suited for a very specific job.
All right, so to really get our heads around these super complex structures, we've got to start with the absolute most basic building block, the single neuron.
So, say hello to the perceptron. You can think of this as the single atom of the entire AI universe. It's the simplest decision maker you can imagine. It just looks at a few pieces of information, decides how important each one is, that's what we mean by weighing them, and then it spits out a simple yes or no decision. That's it. Okay, but here's the catch. A single perceptron on its own is, well, it's pretty limited. It can only solve problems where you can neatly separate the answers with one single straight line. But what happens when you start stacking them up in layers? Well, then you get a multi-layer perceptron, or an MLP. And this is where the magic starts. It lets you go from drawing a simple line to drawing all sorts of complex, curvy shapes, which unlocks the ability to solve much, much harder problems.
And really, this whole idea, stacking simple things to create something incredibly powerful, that's the name of the game here. So let's see how we actually go from that one little neuron to a full-blown network. All right, I know this looks a little intimidating with all the symbols, but trust me, let's just ignore the math for a second and focus on the flow. Information comes in on the left, right? That's the input layer. Then it travels through these hidden layers in the middle. This is where all the real thinking happens. And finally, the answer pops out on the right from the output layer. Every single one of those lines connecting the dots has a weight, which is just its importance, and the network's whole job is to learn how to adjust those weights over time.
And that right there, that's the big takeaway. This beautifully simple layered design isn't just for one type of network. It is the fundamental principle that nearly every advanced AI system we use today is built on.
But, a one-size-fits-all brain doesn't always cut it. For really specific jobs, like being able to see or understand language, you need specialized tools.
So just think about a picture for a second. The pixels aren't just a long, random list of numbers. Where they're located matters. A pixel's neighbors create edges and shapes and textures. A basic MLP, our first model, it just sees a jumble of pixels. It completely misses the bigger picture.
And that's where the convolutional neural network, or CNN, comes into play. Instead of looking at every single pixel all at once, a CNN scans the image with these little filters, kind of like your eyes darting around to make sense of a room. Each filter is a specialist trained to look for one specific thing. One might find vertical lines, another might find a patch of green, another might look for a specific curve. By putting all those findings together, it builds up a rich understanding of what's in the image. Okay, so CNNs are the champs for spatial data. But what about things that happen over time, or in a sequence? Take the sentence, "The cat, which was scared, ran away." The action ran refers to the cat, not the word scared right next to it. To get that, you need a network that can remember what it saw a few words ago.
And that is the job of our next specialist, the recurrent neural network, or RNN. It cracks the memory problem with this really clever little loop. As it processes each word in a sentence, it passes along what's called a hidden state, which is basically a summary of everything it's seen so far to the very next step. This hidden state acts as its memory, giving it the context it needs to understand the whole sequence.
For a long time, RNNs were the go-to for anything language-related, but they had some serious limitations, especially with really long sentences. And then, a new architecture came along and completely changed the game.
In 2017, a research paper dropped with this incredibly bold title. It introduced the world to the transformer architecture. And it wasn't just a small step forward, it was a totally different way of thinking. So here's the magic trick behind the transformer. Instead of reading a sentence one word at a time like an RNN does, its self-attention mechanism, well, it looks at the entire sentence all at once. It can instantly figure out how important every single word is to every other word in the sentence, no matter how far apart they are. That was a breakthrough.
This ability to see the whole picture at once was absolutely revolutionary.
It fixed the long-range memory problem that plagued RNNs, and maybe even more importantly, it allowed for massive amounts of parallel processing. That meant we could train way bigger models on way more data, way faster than ever before. This one innovation is what directly paved the way for the incredible large language models, or LLMs, that we have today.
Okay, so we've seen the blueprints, but how does the house actually get built? How do these networks go from just a random jumble of connections to a finely tuned, intelligent tool?
Well, the learning process all boils down to this 4-step loop called backpropagation. Step 1, the network makes a guess. Step 2, it figures out how wrong it was using something called a loss function. You can think of this like a golf score. You want that number to be as low as possible. Step 3, it traces that error backward through the network to figure out which connections were the most to blame for the mistake. And finally, Step 4, it adjusts those connections just a tiny, tiny bit, so hopefully it makes a better guess the next time around.
And that's pretty much it. That's learning in a nutshell. This simple cycle of guess, check, and correct gets repeated millions, sometimes billions of times. And with every single loop, the network's predictions get just a little bit better until it becomes incredibly good at what it does.
So let's do a quick recap of our AI toolkit, shall we? We started with the MLP, the simple foundation for everything else. Then we met the CNN, our specialist for vision and images. After that came the RNN, the expert in sequences and memory. And finally, we saw the transformer, the modern powerhouse that has completely redefined what's possible with language.
These 4 designs really are the fundamental blueprints behind so much of the technology that is actively changing our world right now. So the real question is, with these unbelievably powerful tools in our hands, what are we going to build next?